Welcome everybody to this year's first colloquium session. And we are very happy to welcome with us Joanne Barstow from your university. Joanne is a very nice colleague with whom I at least like to chat about a few workshops and meetings. We have not had the chance to directly collaborate with each other, but maybe this will change in the future. So Joanne did her PhD at Oxford, studying clouds on Venus. I'm looking here at these people. And her PhD supervisor was Fred Taylor. So she finished her PhD 2011. Then between 2011 and 2016, she was a postdoc at Oxford. Then she was an EIS fellow at the UCL in London between 2016 and 2020. And since 2020, she is an Ernest Rutherford Fellow, lecturer at the Open University near London. And today she will tell us all about Jupiters and methane.
Thank you very much to Peter, Christiana, Ludmilla for inviting me. It's been really nice to come and spend some time with you. And I'm going to give you a little bit of a whistle-stop tour through some of the exciting results that have emerged from the first years of observation with JWST of transiting hot exoplanets. But I could just as easily have titled this The Tale of the Misbehaving Methane, because all of the 4 giant planets I'm going to talk about, there's something not quite right about what the methane is doing in their atmospheres based on our prior understanding. This has been a bit of a theme for JWST so far. Methane is not doing what we think it should. This was working 2 minutes ago. There we go. So there are a lot of people I need to acknowledge before I get started. So 2 of the data sets I'm going to talk about come from the early release science team. So this was a very big international consortium, a completely open consortium that was set up to look at some of the earliest data taken by JWST. And the aim of this was to provide a data set that not only revealed something interesting about its targets, but also taught everybody how to use the telescope and how to handle the data that came from it. One of the data sets came from the GTO 1224 team. That's one of the GTO teams for the NIRSpec instrument. And the other came from a Cycle 1 program led by Tom Evans-Soma. So there are far too many people to mention individually, but these are some of the main people from those teams that I have worked with. Particularly note Agni Banerjee, who was the first graduate student who graduated last year. So I would hope that given the audience I have, I don't need to spend too much time convincing you that observing exoplanets is a good idea. This plot is actually a few years out of date now, but it hasn't changed drastically. And these are the planets that we know about so far orbiting other stars as a function of mass on the y-axis and as a function of orbital period on the x-axis. And because we can't very easily do a simulation of a whole atmosphere with all of its ongoing processes in a laboratory, these objects are in fact our laboratory for answering questions about how planets work, how their atmospheres work, what drives the dynamics and the chemistry in their atmospheres, how they form, how they evolve. And we'll also, as time goes on, get as closer to answering slightly more profound questions like, is Earth rare? Are other planets habitable? Are they even maybe inhabited? But for now, we have this population and we can roughly subdivide them into categories. So at the top of the chart, we've got the Jupiter-sized things, the gas giants. The ones that are over on the far left, these are hot Jupiters. They orbit very close to their parent stars. That means that they have temperatures generally exceeding 1000 Kelvin. Then you've got other gas giants going further out. Many of these are also hot, actually, but not for the reasons that they're irradiated. Many of these are hot because they are quite young, so they are hot with heat that's left over from their formation. We then have the Neptunes, and a category that's particularly interesting for us, the mini Neptunes and super Earths. So these are the things that sit in between the Neptune Earth parameter space. So in our solar system, that is empty, that parameter space. We don't have one of these. We would really like to learn more about them, to learn, for example, where the transition occurs between a big rocky thing and a small gas giant. We still don't really know that. And then we've got a few rocky planets down at the bottom. And you notice the Earth is here. It sits very much on its own still. It doesn't have many friends yet in the exoplanet community. And that's partly because detecting these things is really, really challenging. We tend to forget this now after 30 years of exoplanet discovery, but actually this is a hard thing to do, because what we're trying to do is study something that is next to something that is much, much, much brighter than itself a very long way away. So the vast majority of these objects, we cannot, with the current instrumentation we have, directly study them. Roughly speaking, the ones that we can directly study are the ones that just sit in that very top right corner. And we can only do that, for the most part, if they're still quite young and therefore they're bright intrinsically. For everything else, as yet, we don't really have a chance of directly imaging them. We will start to with upcoming missions like the Habitable Worlds Observatory, like potentially the ELTs as well. Nancy Grace Roman might also start to push discovery space a little bit further, but for the most part, the only way we can study the objects on this diagram is to look at them indirectly. And that obviously means that we're somewhat biased in terms of the objects we can discover. We're biased towards larger planets that orbit in general closer to their stars. By far the most successful indirect detection method we have is the transit method. So this relies on a serendipitous, lucky chance alignment, where at some point during the planet's orbit around its star, it passes directly in front of its star from our viewpoint. And in doing so, it blocks a small fraction of the light coming from the star. If we observe this happening, if we measure the amount of light that's blocked, then we can determine the size of the planet relative to the size of the star. But that's not all, because when that happens, an even tinier fraction of the starlight is filtered through the planet's atmosphere, which is semi-transparent. It will be transparent at some wavelengths and relatively opaque at others. And the part of the atmosphere that we're sensitive to is the bit that sits directly on the dividing line between the illuminated day side of the planet and the night side, the bit that's facing space. And we call this region the terminator. Nothing to do with Arnold Schwarzenegger. It's a different part back to our lunchtime conversation yesterday. So if we construct a light curve as a function of wavelength, so if we determine how much light the planet is blocking at each wavelength, then the tiny differences in the amount of light the planet blocks as a function of wavelength translate to how absorbing the atmosphere is as a function of wavelength, and we get a spectrum. And that spectrum is an absorption spectrum. It's flipped upside down from how you might be used to looking at absorption spectra. So as the transit depth increases, the atmosphere is more opaque. In the regions where the transit depth is relatively small, the atmosphere is transparent. And of course, that means that this spectrum contains the fingerprints of all the different gases that are present in the atmosphere. It means we can determine, therefore, what the atmosphere is made of. And the reason that JWST has been so incredibly transformative for this is partly because it is a really, really big space telescope with has been for previous missions. But the main reason it's been so transformative is that this is an infrared telescope. Up till JWST launched, our space-based access to these sorts of spectra stopped here. And what you get over here is basically water vapor. And you might get some atomic species like sodium and potassium, maybe some metal oxides, but pretty much you're mostly just sensitive to water vapor. And that doesn't really tell you very much about the chemistry of the planet. If you want to understand the chemistry of a planet, you need access to carbon-bearing species, sulfur-bearing species, nitrogen-bearing species, phosphorus, silicon. All of these things have molecular absorption features somewhere over here. So JWST's wavelength coverage is something that is really key for understanding what planetary atmospheres are made of. It has 4 instruments. 3 of them are near-infrared instruments, NIRISS, NIRSPEC, and NIRCam, and the 4th, MIRI, is a mid-infrared instrument. And between them, they give spectroscopic coverage between 0.6 and 28 microns. And so we can therefore detect water vapor, CO2, methane, other various molecules. And not only can we detect them, we can also recover their abundances. We want to know how much of each of these molecules is present. And the reason that we want to know that is that that tells us something about the elemental composition of the planet, how much oxygen, carbon, sulfur it might have relative to hydrogen. And that tells us something about where the planet might have formed. It also tells us something about how the chemistry on that planet operates. It tells us as well, as we look towards smaller and rockier planets, potentially about biosignatures, signs that a planet might be inhabited. So I've talked a bit about how the transit spectrum works, but of course that's not the only time we can get information about a planet during its orbit. For a transiting planet, on the other side of its orbit, it's going to disappear behind the parent star as well. And that gives you another opportunity because you can then compare the combined flux from the planet and the star together just before it disappears. And then when it disappears, you have the flux coming from the star only. So by looking at the difference between those two measurements, you can work out what the thermal emission spectrum of the planet itself is. And for the ones that orbit very, very close to their parent stars, we have the opportunity to study them throughout an entire orbit. So as the day side, the hottest part, most and brightest part of the planet rotates out of view, the overall flux from the system is going to decrease. And then as it comes back into view again, the flux starts to increase again. And this has already told us things about the typical dynamics on planets like this. So planets this close to their stars, they're tidally locked. They're heavily irradiated on the day side and not on the night side. That drives quite fast winds, and those winds can actually move the brightest, hottest point of the planet from the point directly beneath the star and shift it slightly to the east. And we see this phenomenon from phase curves across a wide range of different gas giant planets. So, I didn't tell you about this yesterday, Ms. Miller. So I want to talk now about atmospheric models, because to interpret the data for these planets, you need to have some models. And because I like to be a little bit humorous in some of my talks, I'm going to give you the atmospheric model menu. So this is different types of atmospheric model viewed through the lens of cake. So the most computationally intensive model, which is a bit like the wedding cake of atmospheric models, is a GCM. This is a sort of model that Miller deals with. And this is based on our understanding of all of the physics of atmospheres. So the dynamics, the fluid dynamics of atmospheres, the radiative balance of atmospheres, and also the radiative transfer through the atmosphere itself. And so whilst they're very much rooted in the physics, they are also, understandably, it takes quite a long time to run one of these because there's such a lot that goes into it, and you have to run them for a while for them to achieve steady state. So whilst these are very informative and very good at making predictions, it's not so easy to take one of these, fiddle with it a little bit, and run it again over and over and over and over for a set of different conditions. What you can do slightly more easily, if you ignore the latitude, longitude dimensions and reduce this to something like a layer cake, this might be a one-dimensional radiative convective model. So this is where you've got rid of anything to do with spatial dimension on the planet. All you care about is the vertical dimension in the atmosphere going from the surface out to space. Again, this is a model that's typically based on our understanding of physics, of radiative balance, but it's a little bit simpler and a little bit faster to run. However, if what you really want is something that is the fastest kind of model computation you can possibly think of, because you want to run it thousands, millions of times and compare it with your data set, then what you need is a retrieval, and that's basically pick and mix. So this is a type of model that has very, very minimal physical assumptions that go into it. You can pretty much get rid of all the physics, except for the radiative transfer, because you have to compute what happens if you have an atmosphere that looks like this and light shines through it. But these are very, very quick. They tend to parameterize phenomena such as the temperature profile, such as any clouds that might be in there. But their advantage is that they are very, very fast to compute. And so you can run it lots and lots of times with a variety of different parameterizations with different values for each of those parameters. And then you can compare each of those iterations with your data set. Now, there are a couple of other things that sort of plug into any and all of these models. And Christiana, I really apologise for this one. So we have the chemistry. So many of these GCMs, they have to have a chemical scheme. Radiative convective models often have a chemical scheme as well. That's a little bit like the icing on the cake. So these can be equilibrium schemes that assume the atmosphere is in chemical equilibrium. So if you have an atmosphere that has this stuff in it and you heat it up this much, this is the chemistry that emerges. It can also contain some processes that might drive that atmosphere out of equilibrium. That can be something like photochemistry. It can be transport, either vertical or horizontal. And then, yes, it is sprinkles, the cloud scheme. So many of these will also have a cloud scheme. It can be a full microphysical scheme that accounts for condensation of different species, coagulation, rainout. It can be something that's a little simpler as well that can parameterize any or all of those things. But for now, I'm going to focus on the pick and mix, which is the kind of model that I use, and that's the retrieval. So what we need to set up one of these is we need to have the bulk properties of the planet, the mass and the radius. These are at least a first order known. We also need to have specified the temperature pressure profile, so how that varies as a function of pressure. We need to know what this atmosphere is going to be made of, what gases we're going to put in there, and how each of those gases is absorbing. For that, we need to go to teams like the ExoMol team at UCL, who produce line lists, so absorption line data for gases that are at high temperature. And we might want to put some clouds in there. Now, this could be a cloud where we say, oh, it's enstatite, it's a silicate cloud, and it has this particle size distribution. Or we could be even cruder and parameterize the scattering function with a power law. But we need to say how it behaves spectrally, where it is in the atmosphere. And all of these things go together to make up the model. And pretty much all of these, they are just little knobs that you can tune. So you don't have to make any assumptions about how realistic this atmosphere is. You want to let the data inform what comes out here. And then you take your iteration of your model atmosphere that has a specific set of properties, and you simulate the passage of light through your atmosphere. And you'll get something like this. So in this very crude example, we've got 3 different flavors of model atmosphere. We've got an observation, and one of those is an obviously better match to the observation than the rest of them. Now, clearly, that is very contrived, and it is not as simple as that. So typically what we find is that there's not just a single model that fits, but actually a family of different solutions that provide a good match to the data. So what we want to do really is not to get the one true answer for what our atmosphere is made of. What we want is a statistical representation of the likely composition, the likely structure of our atmosphere. And to do this, we need a retrieval code, because we need to implement this model process, the radiative transfer, lots and lots of times, thousands, millions, and gain this statistical overview of what the atmosphere is like. And the code that I use is called Nemesis, the Python version Nemesis Pi, and it was originally developed to look at Saturn by Pat Irwin at Oxford, and has since been expanded to look at pretty much anything that has an atmosphere, including exoplanets. So how a retrieval algorithm works, the very, very sort of potted history is you have your data, that is an input. You have your physics. In this case, this is the physics of radiative transfer. You can also include some chemical equilibrium constraints as well. You can add physics to this to constrain the process a bit further. You have your prior distribution on each of the things that you want to vary. So typically for exoplanets, that's often the least informative prior that you can put in, because we don't actually know what we expect to be there. But for some quantities, like for example, if you want to allow the planetary radius to vary a little bit, that could be an informative prior, like a Gaussian, because you're pretty sure you know roughly where that is already. Then you have your retrieval algorithm, which I've slightly flippantly called the magic. That can be an MCMC, a Markov chain Monte Carlo algorithm. It could be nested sampling. People tend to use things like DNest4, multinest, ultranest to do this part of the computation. And what you want to get out, if it's worked, is you get a best fit model that hopefully resembles the data. Doesn't always, but hopefully. And what you also want are a series of posterior distributions for the things you're interested in constraining that are narrower than the priors that you put on, because that means you've actually learned something from the benefit. So that's enough of talking about the how. Let's talk about the what and what we found out. So now I'm going to start my little whistle-stop tour of results from different planets. So the first planet I want to look at is WASP-107b. So this is one of the very first objects that was observed with JWST, and this was as part of the early release science program. And it was chosen as the target for a variety of reasons, one of them being that the star has the right magnitude that it is observable with most of the instrument modes that are available on JWST. But also, it's an ideal transit target because it's quite nice and fluffy. It's got quite an inflated atmosphere. So the mass is the mass of Saturn, roughly, but it's a little bit larger than Jupiter. And that means that you get nice, big features in your transmission spectrum if you have a fluffy planet. So this was observed initially with the 3 near-infrared instruments as part of the ERS program. It was then subsequently observed with MIRI, as part of a director's discretionary time program. So it's now been observed with every JWST instrument. It's one of the few that has that extensive a data set. So these are the 4 original spectra covering the near-infrared part. This is without any sort of processing applied to make them agree with each other. So you can see that there are clearly some differences, some offsets between the different instruments, but overall the agreement is good. And also you can see by eye, without having to implement any modelling at all, that there are very clear spectral features in this spectrum. So you've got a series of bumps over here. These are water vapour features. This one is carbon dioxide, and this one over here, this one was a bit of a surprise. So I'll talk about that in more detail in a minute. But really, the quality of the data was absolutely astonishing, this being the first thing that we looked at. So this is one of my favourite figures from Zafarov-Stankolov's paper, and this is the white light curve from the near-spec prism observation. And the bottom panel shows the integrated flux as a function of wavelength and time from the transit centre. So the transit is this purple bit here. You can see where it's darker. And if I was to zoom in, I don't know if you can see on the screen. Can you see the darker purple lines across it? So this was very minimally processed. It's not binned up. Those are the spectral features, and you can just see them in that image. So it's an incredibly precise and beautiful data set, and this was really the kind of first time we sort of went, wow, JWST is going to tell us about. So this is the overall spectrum. This is a figure from the paper that is currently in prep, which is bringing together all of those 5 different observations of this planet. So this is, I think it's fair to say, the most comprehensive spectrum we have of any planet yet. Certainly of any transiting planet, and we've got sodium and potassium and water vapour, that's the blue. This is the carbon dioxide feature, and we've got carbon monoxide sitting just to the right. And this thing here is sulfur dioxide, and this was a bit of an initial surprise because we went, this is a gas giant. It's a thing that's basically made of hydrogen and helium. Why, if there is sulfur there, is it sulfur dioxide? Why is it not in the form of H2S? And that told us right off the bat that some of our assumptions going into this were wrong. It told us that actually photochemistry is really important on these objects, because what we think is happening is that you've got all this water vapour. It's very, very easily dissociated by ultraviolet photons in the upper part of the atmosphere. And the products from that dissociation can react with H2S and form SO2. So we have SO2, and the reason that we wanted to look at this planet with MIRI is because we wanted to verify that SO2 detection, and we did. So we have a beautiful double-peaked SO2 feature in the MIRI dataset. But the other thing that's a bit weird about this spectrum is there is no methane. We do not see methane on this planet. This planet is about 1,000 Kelvin. So it's in the temperature range where we would expect to see some methane if this atmosphere is solar metallicity, solar carbon to oxygen ratio, and in chemical equilibrium. And we don't see it. So maybe this means that the planet has a lower carbon to oxygen ratio. But actually, this is not the only thing that is a bit tricky about this planet. So this being one of the very earliest data sets, and with a big international team looking at it, rather than just applying one retrieval code, we thought, well, why not let everybody have a go? And we applied 10 different retrieval codes to this spectrum. And of course, what we wanted to happen was for everybody to go away and run their retrievals, and for us to come back together and go, oh, look, they all agree with each other. If you thought that was going to happen, you've never done a retrieval before. So this is the result from the Chimera retrieval that Luis ran, compared with the Chimera grid model. So the grid model is a chemical equilibrium model with the added photochemistry to produce the SO2. So these are vertically varying profiles of the different gases, water vapor, sodium, potassium, etc. And then these are the retrieval results, assuming a well-mixed atmosphere. And the agreement between those is pretty good, which you'd hope, because they are based on what is essentially the same model. But if you then compare it with the results that I got from the Nemesis run, the colored posteriors, they're not the same. Why are they not the same? And just to stress that, and Chimera and Nemesis had been heavily benchmarked against each other previously. So we would expect them to come up with something similar. And it wasn't Chimera and Nemesis that were different. All 10 of the retrieval codes came up with slightly different answers to each other. There was a spread of values. And we started to worry about that for obvious reasons. And what we eventually realized is that we thought we'd picked a perfect planet for this first observation. And in many ways we did, but in one very important way we didn't. But it's a way that we couldn't possibly have known until we actually looked at it with this telescope. So these are now two spectra that I took from my best fit posterior draw, and they have a water vapor abundance that differs by a factor of 3 between them. But the spectra look almost identical, particularly over the nearest wavelength range, which is the instrument that has the highest precision and the most water vapor balance. So this drives quite a lot of the retrieval, but it's actually pretty similar across the whole wavelength. Why? How can you possibly have spectra that have 3 times factor 3 difference in water vapor abundance that looks so similar? Well, it's to do in part with the amount of water vapor you have. So regardless of which retrieval code you look at, of which answer, this thing has about 1% water in the atmosphere, give or take, by volume. And if you increase the amount of water a little bit from that 1%, then you're adding absorbing gas, so you're making your absorption features bigger. But what you're also doing is you're making your atmosphere heavier, because water has a higher mean molecular weight than hydrogen, which is the bulk of the atmosphere. And that has the opposite effect. That flattens your features because it's physically compressing your atmosphere. Sorry, the microphone. 2 seconds. There we go. It's hopefully back now. So you've got 2 competing effects. One of those effects is increasing the size of your feature. The other is shrinking it. And then you've got lots of other things that can change slightly, like the temperature pressure profile, like the clouds that you might have put in. And those can make it basically perfectly cancel out. So you have a flat bit of likelihood space for this planet. So you have a range of perfectly acceptable solutions that's quite big. And it is not something that you can fix. It's a property of the planet, and you can't fix it with just retrievals. So we have run, as part of this paper, about 1 billion individual models across all the retrievals. Those are the individual spectra from the different retrievals, and that is the spectrum that has taken all of those models all together. So that is the model fit. We'll probably never do this again for any other planet, but we learned an awful lot by doing it. It's the most comprehensive analysis ever. And we have learned something very useful apart from just about process. So what we've basically got, if we take the range of solutions that are provided by the free retrievals and we compare them with constraints from equilibrium grid models, from equilibrium retrievals, and from the predictions of interior structure models, so by combining all those modelling approaches, we come up with quite a nice answer. So this is basically Saturn. It is a hot Saturn. It's a 10 times solar metallicity Saturn mass planet, orbiting very close to its parent star. And it actually does make sense, but it's really important to take home that even in the era of this exquisite data, we still have these situations where we get degeneracies in retrievals, where multiple solutions will give you just as good a fit, just as good an answer. And so you need this context and this sanity check from all of the different types of model that are available to us. You cannot just assume that a retrieval yields the one and only perfect truth for this planet. I'm hoping that this paper that Louise is leading will be published soon. I've been saying that for quite a while. It's one of those papers that takes years because of the amount of in-depth work that needs to be done, but I'm hoping it will come out later this year. So, WASP-43b, this is my next planet. So this is another early release science target, and it's like the complete opposite of WASP-39b. It is a terrible transit target. It's quite a dense planet, and that makes it a really awful transmission spectrum target. But it has a very, very short orbital period of only 19.5 hours. So that means it's a brilliant phase curve target, because you can look at the whole orbit of this planet in about a day. And incidentally, I did actually look up once what sort of thing you might be able to accomplish in 19.5 hours. And it turns out that an extended cut Lord of the Rings and Hobbit marathon would actually take you about 19.5 hours. So if the mood should take any of you to do this, you can do it and think, oh, I'm spending a year's worth of time on WASP-43b doing this. So we stared at this object for 28 hours with JWST, and with the mid-infrared instrument MIRI. And we obtained spectra. These are binned to 4 different phases on the planet. So this is phase 0, the night side. We've got the evening terminator here. This is the day side, and this is the morning terminator. And we've got really dramatic temperature differences between the day and the night side, about a 650 Kelvin difference, which is not entirely unexpected. We know that this thing is tidally locked. We know it's being highly irradiated on the day side. But what we didn't expect, what was particularly strange about this, is that the shape does not change between those spectra. You can see that the amplitude does, and the overall brightness temperature does, but the shape does not really change. And we thought that's weird, because what we would expect to be happening for this planet is for the day side to have spectra dominated by water vapor, and any carbon in the atmosphere to be in the form of carbon monoxide and carbon dioxide. But on the night side, this is quite cold, relatively speaking. This is less than 1,000 Kelvin. We would expect to see methane. Where is the methane? And the answer is not there. So we performed retrievals with 3 different retrieval codes this time on those spectra, and we get pretty good agreement, and they all agree that yes, we've got water vapor absorption in all of those phases, and there is no methane absorption at any of those phases. And in particular, on the night side, where we would expect, given equilibrium chemistry, we'd expect the methane abundance to sit somewhere over here, we actually get a pretty stringent upper limit that says it's definitely much less than that. It's less than 1 part per million of methane. So what on earth is going on there? Why is the methane not there? So we think that this can be attributed to atmospheric dynamics. So given this planet has this huge day-night temperature gradient, this is going to force circulation, it's going to force winds. And if your winds are fast enough, what's going to happen is that you've got a parcel of air that's rich in carbon monoxide coming around from the day side, coming onto the night side, and chemical reactions are going to start that will convert that carbon monoxide to methane. But if this parcel of air doesn't spend long enough on the night side for the methane to build up to detectable levels, you'll never see the methane, because by the time it's started to get enough methane, it's gone back round to the day side again. So what this does is it gives us a constraint on the wind speeds on this planet, because we know how fast the chemical reaction should be proceeding to convert the CO to the methane. And that tells us that we've got probably about 5,000 mile an hour winds going on this planet. And that is what is driving this disequilibrium chemistry. It's a process that we actually call quenching, where the atmospheric composition from one part of the atmosphere dictates what the atmospheric composition is everywhere because of circulation. So we've got water vapor everywhere, but no methane. And the other thing that we've determined from the phase curve is that the cool night side is probably cloudy. But annoyingly, we can't say what the cloud might be made of, because there are no spectral features that would indicate a specific cloud. But if you compare the phase curves to GCM predictions, it is much better reproduced by cloudy GCMs than it is non-cloudy GCMs. So there's probably cloud, but it's not producing distinct spectral features that we can therefore look and say it's definitely this cloud.
What's the sound velocity in miles per hour to compare with?
Oh, I don't know off the top of my head.
Well, it's supersonic, isn't it?
Yeah, it is supersonic.
Vastly supersonic.
Yeah. Yes, but it is supersonic. It's ridiculous, really, but that's how fast it would have to be. Okay, so my third planet is the one that came from the GTO program I was part of with NearSpec, and this one has got quite a lot of press attention over the last couple of years. So this is one of the most highly inflated planets out there. It's variously been referred to as a super puff, the popcorn planet, the candy floss planet. It has an awful lot of nicknames, because it is very, very, very highly inflated. So it's a Neptune mass planet that is pretty much the size of Jupiter. So it's as if somebody took a Neptune mass thing and pumped it up. But this didn't really make a lot of sense, because this planet isn't really that hot by comparison with some of the other hot Jupiters. So inflation is something that's pretty common in hot Jupiters, mainly because of the higher radiation they experience. But this one, it didn't really make so much sense for. So we started out with a slightly mysterious object, and we observed it using the G395H prism on the NearSpec instrument, which gave us a spectrum between 2.8 and 5 microns. And there are plenty of familiar things popping up here. So this is the edge of a water vapor feature. Here's the CO2. Here's the SO2 again, like we saw on WASP-39b. And importantly, here is methane, where it's supposed to be for the first time. Excellent. So we found the methane. It's there. This is a demo that I set up for the Royal Society Summer Exhibition. It's actually a jigsaw, so some of the kids played with it. This is a slightly nicer plot version from the paper using David Singh's model, ATMO. But what you will notice about the methane is that you're only really seeing that very strong Q branch in the middle. So it's mostly being completely washed out by the water vapour, and there's actually not very much of it. So it's about 1 part per million methane, which is great, we found it, but it's still not quite right because it's about a factor 100 less than we were expecting. Now, there is methane, but there isn't enough of it. And reassuringly, another team at exactly the same time had got data from a different instrument that covers the same wavelength range from NIRCam. And we independently worked on our own data sets. We coordinated publication, but we each arrived at the same conclusion. We have about 1 part per million of methane. So this is the observation this time from the NIRCam team. You'll see the methane is there. They also analysed the data from the MIRI observation, where you have this nice silicate cloud feature as well. So there is no methane observable in the MIRI spectrum, but that's not a huge surprise because it sits around here where you've got that big SO2 feature. So it's probably hidden by the sulfur dioxide. So what might be going on for this planet? Why is the methane there, but in such small quantities? Well, we think that this is to do with the planet's orbit. So this planet has a small but non-zero orbital eccentricity. And that means that you've got varying tidal forcing as it completes its orbit. And we have a very similar object in our solar system, at least that undergoes something similar. So we have an example, and that is Io, Jupiter's moon Io. So Jupiter's moon, Io, is heated by tidal forces. And that's the reason that it has so many volcanoes, because of that internal heating. And this can explain WASP-107b's inflation. If you've got lots of tidal heat being deposited in the centre, it can explain why it's so puffy. And it can also explain that relative lack of methane, because you've got a hotter interior than you thought you did. And that's going to drive relatively vigorous vertical mixing because you have a hot interior. That's going to draw up methane poor, hotter gas from deeper in the atmosphere into the bit of the atmosphere that we see. So this is this was kind of a really nice coherent story now for this planet. You've got a planet with an eccentric orbit, and this produces inflation, a hotter deep atmosphere, and also correspondingly a lack of methane in the atmosphere. So my final gas giant planet that I want to talk about is WASP-121b. This is my favourite because it is a truly ridiculous planet on every possible level. So it's an ultra-hot Jupiter rather than just a hot Jupiter. It has an equilibrium temperature nearly 2,500 Kelvin. It's orbiting in a very short orbit, just over 30 hours, around an F-type primary. So you can imagine just how highly irradiated this thing is. So it's very, very fluffy, and it's an ideal phase curve candidate. So this is great because we can get a good transit spectrum and a phase curve from this planet. So this is the phase curve observation that we got from Tom Evans-Somer's programme. These are the raw broadband light curves. So these haven't even been corrected. And that's what they looked like. So you can see that there's a little bit of a drift between that eclipse and that eclipse. So there was a little bit of instrumental drift that we could correct for. But that is just one of the most beautiful data sets I've ever looked at because it is so clean and so precise. So one of the things that from a modelling perspective I found particularly interesting for this planet is that because it's got such an extreme day-night temperature contrast, it's well over 1,000 Kelvin. That actually means that the terminator region, that bit of the atmosphere that's between the day and the night side that we're sensitive to in transit, it means that you can't really assume it's the same everywhere anymore. Because the day side is so much hotter than the night side that the night side is actually physically smaller than the day side. The scale height is that much smaller that it's almost like an egg-shaped thing. It actually collapses. And that big temperature gradient is not just the temperature profile and structure that it affects, it may also affect the chemistry. So in theory, you could have different chemistry on the path that the light takes through the terminator. And that's something that we need to consider. So the first thing that I looked at was not the phase because it was the transit. And I introduced a new parameterization for my model, for the Nemesis model, that splits the atmosphere at the terminator into day and night components. And that has the advantage that it allows you to model that difference in temperature, but also to allow for differences in chemistry across that boundary. And so having applied that to the transit spectrum, this is what we get out. So the temperature retrieval gives you an inverted temperature profile on the day side. That's what you'd expect. So you've got this inversion where the temperature increases as a function of altitude. On the night side, we assume that there is no inversion because there is no irradiation coming from the top of the atmosphere. And we recover abundances for carbon monoxide, this feature over here, silicon monoxide. It's the first infrared detection of gaseous silicon monoxide in a planetary atmosphere. And we've got water vapor. So but this is what's particularly interesting because we don't see dayside water vapor, it's on the night side. And that makes sense because this thing is so hot that on the day side, the water vapor is actually going to start to be dissociated. It's going to be breaking apart. But how can I possibly say this just from looking at one spectrum? Well, this is why I know the water's on the night side and not the day side. So if we look at the CO band, this is what the light is encountering in the CO band here. So the day side atmosphere and the night side atmosphere, they've both got a lot of CO in. But the day side atmosphere being hotter is much more extended than the night side atmosphere. So it's opaque out to a much higher altitude. So you pretty much don't see the night side component, you just see the day side. So this is like a thermometer for the day side, this absorption band. It tells you what the temperature is on the day side. And the same for the SIO, it's present in both. So it's a thermometer for the day side portion. But it's different for water. If water is being dissociated on the day side, then that opacity source is being removed. And there isn't anything else in that wavelength range that's absorbing. So what you end up with is a transparent window region in that wavelength range on the day side. So you have the opposite case here. The opacity surface on the day side is actually much deeper down in the atmosphere this time because you've removed your absorber. So you see, for the first time, this night side portion, you're actually sensitive to it. And the reason we know that it's the night side is that this is water at 1,000 Kelvin, not 2,500 Kelvin. The spectroscopic features are sufficiently different at those temperatures that we can say this is 1,000 Kelvin water. So from a transit, we have actually been able to directly say for the first, this is water vapor dissociating on the day side of the planet. So I really enjoyed working on that. It was a fun paper, but it gets even more fun because we also have the phase curve of this planet. So this was published last year, and the day side spectrum and the abundances and the temperature profile are really consistent with what we inferred from the day side portion of the transit. But the night side is a little bit more confusing. So unexpectedly, we're not seeing absorption by water vapor in that spectrum. We're seeing absorption by methane. And this was kind of the irony, right? We've not found methane in so many places where we were supposed to find methane. And then we have found methane in a place where we really weren't supposed to have found methane. So what is going on here? Why is there methane on this incredibly ultra hot planet, even if it is on the day side? So it's not completely nonsensical. So the hypothesis for this case is that at higher pressure, you also expect to have more methane. And if there is vertical circulation on the night side, you could be bringing up enough methane from the deep atmosphere for you to see it. But we would really like to know more about what this methane is doing. We want to know potentially how far around the planet does methane extend, because we're not seeing it in the transit spectrum. So it's apparently not there close to the limbs of the planet. And the other thing is, this should be, if we've got methane in those quantities, you should be able to see it with another instrument on JWST, MIRI. The mid-infrared instrument should have a lovely big methane feature right there. So far, nobody has yet obtained time to observe the night side of this planet with MIRI. Let's wait and see whether that happens in the next month or so. So I produced fits, I did a joint fit of the day side spectrum and the night side spectrum from this phase curve here. The reason it had to be a joint fit is that even on the what we call the night side spectrum, there is still going to be a tiny little sliver of day side crescent that is visible at that phase, because the night side phase is when the transit is happening. So from that joint fit with a day side model and a night side model, I extrapolated that then to all of the other phases in this phase. And I think you'll agree that that is actually a remarkably good extrapolation, given that these were the only two spectra that were actually being fit. So it really seems to be the case that this planet is two-faced. It has a very different day side to the night side, and it's very well represented by just those two components. It's not as if things don't change gradually on this planet. It's very much a two-faced planet, and there's a lot more that we need to learn about this object. So to recap this one, we've got CO and SiO on the day side, methane apparently on the night side from the phase curve. The transit tells us about the water vapor dissociation in the upper atmosphere, and towards the end of last year, some other data were also published this time from the NIRISS instrument, that's at the shorter wavelength end of JWST. And that's interesting as well, because that hints that there might be a component of reflected light at the shortest wavelengths on the day side, which implies that there has to be a cloud on the day side of this 2,500 Kelvin planet, which is even more bizarre. So there is a lot of that still needs to be done working on this planet that I'm very much looking forward to seeing how it all pans out and also getting involved in. So what about rocky worlds? Just for the last couple of minutes, I want to talk a little bit about the future. So you might be thinking, why am I just talking about gas giants? Why am I not talking about things that are more like the Earth? Well, at the moment, it's because they are just a lot harder to do. So rocky planets are smaller, of course, so they block less starlight overall, but the main thing that really is a problem for rocky planets is the signal in the transit spectrum. So the scale height of a rocky planet is always going to be much, much smaller than the scale height of a gas giant. And that's mainly because of what their atmospheres are made of. So if you've got a secondary outgassed atmosphere, it's going to be much heavier than a gas giant atmosphere. That's going to reduce your scale height. And if you're interested in looking at things like the TRAPPIST planets, which are temperate, the fact that they're such low temperature is going to reduce your scale height even more. So your signal is very, very small. But there are a handful of rocky worlds, of super Earth-sized worlds, that we have been able to extract a spectrum that still needs verification, but something that actually does look like it has a signal in. So my student Agni worked on the spectrum of L9859d as part of his PhD. So this is a 1.5 Earth radius planet in orbit around an M dwarf. Like WASP-107b, it has a slightly eccentric orbit. And what this spectrum indicates is that the atmosphere is really dominated by absorption from sulfur gases. It's H2S and SO2, or a combination of the above. And what we think might be happening here is that what we're actually seeing is an exo-Io. It's a rocky planet that has a lot of internal heating. It's therefore driving extreme amounts of volcanism, and you have a lot of sulfur gases in the atmosphere. And this is not yet confirmed because the detection of the atmospheric species here, it hasn't yet reached the sort of gold standard 3 sigma threshold. We need further observations to do that. But what is reassuring is that the innermost planet in the system, L9859b, has very similar features. This is also a rocky planet in an eccentric orbit. And before you say, oh, hang on, doesn't that worry you that it's the same system, isn't it, from the start? I don't think there is any known star that has sulfur dioxide absorption features in its atmosphere. So I don't think it's anything to do with the star. But it is definitely something that we want to follow up. There are other data sets that have been obtained for this planet. They are not yet published. So maybe that will reveal whether this is in fact an exo-Io or not. So where do we go from here? This is sort of a snapshot of where we are after the first few years of JWST. So we want to fill in this diagram. These are the targets from cycle 2 and cycle 1. As a function of planet radius and planet mass. We're doing a pretty good job of covering that parameter space already. We added on cycles 3 and 4 and subsequent cycles, hopefully we'd be populating this even more. There's lots of scope for model development here. So JWST has already shown us lots of inadequacies in our models. For example, the lack of the photochemical network that meant we didn't predict the SO2. That's been remedied now. We're having to introduce different ways of setting up our retrieval models to account for things like that huge temperature gradient on WASP-121b. But then obviously we're also looking forward to new observatories. So the ELT is one example that will achieve first light in the next few years. There is also Ariel. Ariel will conduct a survey of 1,000 transiting exoplanet atmospheres. So this is the sort of thing that will start to give us not just detailed information about some targets, but a population level analysis of these objects. And then finally, the thing that I am currently most excited about for the future is Habitable Worlds Observatory. So this is going to be NASA's next big flagship mission. It's going to launch in the mid-2040s, but the planning for this, the science case design, And the telescope design and instrument design, that's happening actually now because they need to be well ahead of the game to avoid the sort of delays that JWST experienced. So the review of this is going to take place in 2029. It's not actually that far away. So this is the time to be sort of writing papers and white papers and saying what you want this telescope to do. And here we've got a nice sort of mock-up of what Earth, Venus, Jupiter and Saturn might look like with a HAB-WELS-like telescope. And obviously, many people are very interested in this, but I'm pretty interested in these. So exo-Jupiters and exo-Saturns, not like the hot Jupiters, although I'm having an enormous amount of fun studying them right now, they are not very good analogues for Jupiter and Saturn. So we need to start pushing down towards those cooler gas giants to really understand the giants in our own solar system. I will summarise there. So I think you'll agree that JWST is really transforming our observations of transiting exoplanet atmospheres. And the current benchmark planets we're looking at, they're already revealing surprises. We've got a very well-established process for retrieval modelling, but things do need to be updated and enhanced. And retrievals need to be viewed in the context of all the other kinds of modelling that we have at our disposal. So I hope that based on our sort of experience with the ERS, that there'll be a little bit more collaboration and kind of working together across different modelling communities going forward, because it's actually really important to have that overall holistic picture of what's going on. Small planets are currently really hard. Robust biosignature detections probably aren't on the horizon just yet, but 20 years' time, the picture could look very, very different. So we've got many more planets to explore, and the ultimate goal is really to understand these objects, not as individuals, but as a population. And that's what's going to really teach us how they work.
Thank you very much for this very nice information. Right now, exoplanet atmosphere. These questions. I encourage the younger people to also ask something. There are questions from younger people. Sorry, Peter. First, Nidhi.
Thank you for your talk. My question was about the horizontal wind jet. So you mentioned WASP-43b has a supersonic wind jet that homogenizes the carbon chemistry. I was wondering why a planet like WASP-121b would not have something similar. Why does it have the two-faced structure?
Yeah, it does seem so. It's not entirely unexpected because it does seem to be that the circulation kind of breaks. There's a sort of break point as you go up in temperature. So. And we know this in part because of we've got Spitzer phase curves of quite a large number of planets that allow us to study how far that hot spot is offset from the substellar point. And so for planets that are in the kind of WASP-43b-ish temperature regime, we see quite big offsets, and that implies that you've got this super rotation circulation that's quite efficient. That starts to go away as you get to hotter planets. So around the sort of 2000-ish Kelvin mark, those hotspot offsets start to disappear. And so that's borne out by WASP-121, so it has a much smaller hotspot offset than 43. So we think that what's happening is it's a kind of regime change from that super rotation to something that's more a substellar anti-stellar flow. So more of a global flow, and it's less efficient. I think it's almost as though the temperature difference is so great that nothing is efficient enough to perform that transport. But I don't fully, not working on Ludmilla might be able to say more about I don't know if you know about the GCM.
Actually, I would refer to Iona because in principle that's Iona's work, and that is magnetic field coupling. So the idea is everything is so dissociated on the day side that you have basically plasma flowing in a gas phase environment. And now you suddenly in a planetary magnetic field, there's coupling between those two, and this impacts the flow, which in turn also maybe impacts the chemistry, and that's basically what Iona has plugged in there. And she's currently has a paper review on this, how to do this for the other process. Now the next talk is the next question.
So on the question, I have a question on WASP-121b. You said we detected SIO on the day side.
Yeah.
And the day side is actually quite high in temperature. So shouldn't SIO dissociate at that high temperature of around 2500?
No, it's reasonable, no, it's reasonably, it's got reasonably strong bonds compared to water. You'd expect water to dissociate much faster than that.
SIO is like CO.
Yeah, it's like CO, so they're pretty robust. So you see both of them together, you'd expect them to stay. So it's not hot enough to dissociate everything. At least not at, I mean, as you go higher up in the atmosphere, things probably aren't, like to the sort of thermosphere level, you will get much more dissociated. Things will start to get ripped apart. But at the level that we're sensitive to, no, you do not expect SIO and CO to be dissociated, but you do expect water to be. And you also expect H2 to be. So rather than having, it's still a hydrogen-helium dominated atmosphere, but it's atomic hydrogen.
I work in like metal oxide, so I know TiO2 and Al2O3 can survive at that high temperatures, but
SIO is also pretty robust at those temperatures.
I have a question to your benchmark, to your retrieval benchmark. You said there are actually surprising differences between the codes, and then you explained them. Well, you know, we have these degeneracies, but I wonder, you know, a good MCMC algorithm should actually beautifully resolve this, because it should give you, if you have a well, if you can have some good fitting models here and there, it should give you the full distribution. So I'm worried that there's maybe more behind that, you know, when you let it run long enough and the model is the same, then I would hope that despite these degeneracies, you should get the same
you should just get a broader,
a very flat, or say limited but flat distribution. But so maybe the problem is in the MCMC algorithms?
I mean, maybe partly that. I think actually what's going on is that, so it may be that, so I think most of us are using multi-nest rather than, some of them use MCMC, most of us use multi-nest. Multi-nest can be overconfident about its solutions, so it's a known problem, so it might partly be that. I think also though, you're right, but that sort of assumes that all of the radiative transfer models are behaving in truly exactly the same way. And we know that they're not at the levels of precision that matter for this. So personally, what I think is happening is that, yes, you've got this flat likelihood region. It's not actually flat over such a big range as if you look at the range of values you get from all the codes, it's not actually flat over that sort of range. They all overlap. But everyone's made a slightly different decision somewhere in the implementation of the radiative transfer that just knocks it into a slightly...
So these differences amplify, or no, say the degeneracies amplify the slight differences that there might be.
Yes, I think that's it. So because it's degenerate, if you had data that were really constraining, it would matter a lot less, all those little differences in the implementation. So, I mean, to give you an example, we investigated, we've gone down a lot of rabbit holes, as you can imagine, trying to diagnose this. And one of the things that we tested out was whether it matters whether you're retrieving a reference radius or a reference pressure. Because the first order, so I guess for the benefit of people who aren't sort of really embedded in this, in transit, when you're retrieving something for a transit, you can't just fix the radius or the radius pressure coordinate, because your measurement of the radius comes from a transit. You don't know what pressure level in the atmosphere that radius corresponds to. So you have to let one of the two things vary. You have to either say, I have a fixed pressure coordinate and I'm going to retrieve the radius at, say, 10 bar and let that vary. Or you say, I have a radius and I'm going to retrieve the pressure level that radius corresponds to. Or you can actually do both. It's not completely degenerate. And the reason it's not completely degenerate is that depending on if you're varying the radius, you change the gravity in a slightly different way to if you're retrieving the pressure, because when you calculate your gravity, you're calculating a mass that is enclosed within a radius. If you change your radius, you change the gravity in a slightly different way to if you're changing your pressure. It's really subtle. In most cases, it will not matter. It matters a little. It doesn't make a difference here because it's this is what I mean, right? It's at that level. most people think, well, why does it matter? It shouldn't matter. It does matter, but it only matters at these kind of really tricky edge cases. So actually what we've done for this is we've actually retrieved both. And you get a two-dimensional posterior that's basically a diagonal, but it does have a maximum. So that's just one example of.
There are more questions.
I'll keep it short, but I've seen in two of the spectrum, the fit has some discrepancy of the data. In some, let's say, some peaks are not represented. How do you treat this? Like, how do you, for example, here, the last one, actually? What is that planet?
Oh, this is because this is
3.5, there is something, and
these are really quite noisy. These are low signal to noise. So I don't actually think there are any real discrepancies there. You were talking about.
yeah, the part at 3.5. I think in the other planet it was at longer wavelength at 10 micron. There is some.
Oh, okay. If you're talking about WASP-39, that's because yes. So we can't. Yeah, we struggle to fit the very longest wavelength then on WASP-39.
My question is more general. Like, how do you discuss this if you present this and say, okay, are these differences missing physical elements, or
in this case, I don't think so. I'm pretty sure this is just noise. I think it's just I know it looks like it, but it's a couple of points. I don't think that's statistically significant. For WASP-39, we do discuss it. So one of the things we think it might be for WASP-39, we don't think it's clouds. Well, we think there are clouds, but we don't think that's the reason for the lack of goodness of fit, because it doesn't look like there's a silicate feature. So what we think that might be is it's unaccounted for infrared excess from dust in the system, which only starts to really matter when you get these. But there are, I can go, if I go back to the detail of WASP-39, some of these things may also be instrumental because it's still quite early days, even though it's a few years in. I'm still understanding it. Sorry, let me find it. Don't know if it's zoomed in enough.
here like 2.2 or something, the data is lower, like we have more absorption, right? For example.
Yeah, no, lower is less absorption, but yeah. So that could be one of the things that could be is that we're even more complicated. So I've talked about there being differences for WASP-121 along the line of sight. For these planets like this, there are probably differences between the east and west terminator. So we are modeling that very crudely by saying that we have a fractional cloud coverage. But if you go into more detail in that and you allow the temperature profile and potentially the chemistry to be different, that can also impact. So this is not the final answer, I think, for any of this. There are still improvements that can be made. There are still papers that are being written to look at exactly these problems. But that could be attributable to that. I will say that we've got, you might think that we've already got enough data for this planet. Louise didn't agree with that. So we've actually got 2 more spectra coming. One of them is down already that covers this little chunk. So this is using 2 of the other near spec prisms, which are shorter wavelength coverage, but higher precision nearest. So we've actually got another spectrum covering this bit that is down, and we'll have another covering the adjacent bit, not for a while, in a few months' time. And they will hopefully try and allow us to sort of look at this again and resolve, is this because our models are inadequate, or were we just a bit unlucky with a noise draw? But there are other little things that so there's what looks like a peak at maybe 4.9 microns in G3955H. That pops up in a few different things. We don't think it's real, but there's a couple of other little spiky things that may or may not be real. You know, if you look at them funny, they could be a Q branch, or it could just be random. So yeah, there's still an awful lot of work that needs to be done to sort out where our models are not quite as they should be.
Maybe one final question.
Yeah, can I just follow that up? So am I understanding this correctly? So the planetary disk is, or the planetary observation is seen as homogeneous. So the one-dimensional model fitting the entire spectrum for something that is not, yeah, okay.
Yeah, and that's the other thing, of course, is that even at the transit fit level, that is an oversimplification.
Okay, understand.
So that's what Hannah's group at Bristol are working on, is trying to fit the actual light curves with a model that is not just a circle for your planet. It's can have a different shape.
Yeah, because especially for 39, we know that it's very non-homogeneous.
It's highly asymmetric.
Yes.